Let's put those words into context. What does that word kinetic mean? Do we know what that word means? Or kina, the prefix even, kina, what that means? The prefix kina means motion or movement, okay? So we're talking about the motion of molecules, right? The movement of molecules and the theories behind that. The theories that we're going to go over today are assuming that we're dealing in ideal circumstances. We call them ideal gases, which means they behave exactly as they should. That means there's not extreme pressure and temperature situations, or there's not attractive forces that are outside of that control. It's just everything's behaving ideally. So that's really where we're at for right now. This is ideal world, okay? So there are 5 postulates that we talk about in terms of kinetic molecular theory, how things are supposed to behave. So number 1, it says gases consist of a large number of tiny particles that are far apart relative to their size. Okay, far apart relative to their size. So when we say far apart, that could be on the nanometer scale, right? Times 10 to the negative 9th of a meter, right? That's really not far apart. But if their radius is 1/1000th of a nanometer, right, then that means it's 1,000 times its length away. Okay, you know what I'm saying? Relative to their size, gas particles are farther away. Gas particles are much farther apart than liquid or solid particles. We're good with that concept, right? Gas particles have more room. And the reality of gas in general is that most of the volume of a gas is empty. Right? Most of the volume of a gas is empty. Because what do gases do in terms of their space? If they're put into a container, what do? Do they stay centralized in one location? Yeah, they fill the container, right? So if I put 10 gas particles into, let's use some comparative sizes, right? So if I put 100 gas particles into something the size of like a soda, right? A pop can, 100 particles in there. Okay, they'll move around, they'll fill up the space. If I dump those same 100 particles into a 2-liter container, do we automatically multiply the particles? No, but my volume increased, which means those particles just have more room to spread out. So again, most of the volume of what we consider gases is really empty space. So when we say the volume of the gas, it's really just the volume of the container. And we assume that the gas has been diffused through that entire container. Okay, so large number of tiny particles that are far apart. Number 2, it says collisions between gas particles and between the particles in the container are considered elastic collisions. So let's highlight that. Let's circle that. Whatever you want to do with that word, elastic collisions. That might be a new one for us, okay? And it's really a physics term, but an elastic collision. Do we have any thoughts on what it might mean to be an elastic collision? Elastic collisions mean when they collide, they bounce apart, right? So that's an elastic collision. An inelastic collision would be they collide and they stick together, right? So these collisions are considered to be perfectly elastic, which means when they collide with something, there is no loss in kinetic energy. Okay, so that means if my object is moving, let's say with 100 joules of kinetic energy, and this one is at rest, let's think what would happen. Okay, if this one's moving at 100 joules and this one's at rest, what will happen after that collision? Do we have any thoughts? Can you describe to me what's going to happen? What's going to happen to the second one? Is it going to move? Is it going to not move? Let's draw it out and see what we think, right? Here's the first object. Here's the second. If this first object moves with 100 joules of kinetic energy and this one is at rest, what will happen after the collision? What will the red ball do? It'll move. In what direction?
So whatever direction it's pushed.
Yeah, to the right. With how much energy? 100 joules.
Oh, I thought it was.
Right? 100 joules. So if we have 100 joules of energy, and it collides with something that's at rest, this one now comes to rest, and this second object takes all of that energy with it. Right? There's a couple of assumptions that we have to make for that to be true. They have to have the same mass. okay, in order for that to be true. But that's considered a perfectly elastic collision. What we think about with that is when you're playing pool, right? And you hit the cue ball, and the cue ball hits another one. The cue ball is supposed to come to a stop, isn't it? Right? On a perfectly hit pool ball, that cue ball is supposed to come to a stop. That's a perfectly elastic collision where all of that energy is transferred from one to another. So that's what we consider here, that our collisions are elastic. Okay? So when they hit each other, they're not going to stick together, they're not going to slow down, it's going to be perfect. All right, number 3 says gas particles are continuous, rapid, and random motion. They all possess kinetic energy. Okay, we see that word see that prefix kina again, right? Energy of an object in motion, kinetic energy. But gas particles are continuous, rapid, and random motion. I would even add one more describer to that, one more descriptor to that. They are in continuous, rapid, random, straight line motion. Okay, I'm even going to add that in there. So let's put that descriptor in there, is that it's not only rapid and random, but it is straight line motion. So that has to be true until what? They are in continuous, rapid, random motion until what happens?
Until they bump into something.
Until they bump into something. And what are some things they could bump into?
Well, if the container's other,
It could be the container. It could be other particles, right? Those are the things that it could bump into. And when it does that, right, it will collide and bounce off and it will keep moving, right? That motion and the collisions of our objects with walls, that's what causes pressure, right? The collision of gas particles with the walls of the container are what we know as pressure, how much force is being applied. And there are things that we're going to talk about that affect the pressure, that affect the energy of our system. But those are what we're talking about with our gas particles. They're small and they are in continuous, rapid, random, straight line motion. Okay, number 4 says there are no forces of attraction between gas particles. Okay, this is what we consider ideal, right? When gases are behaving ideally, they're not going to come together and be positive, negative, stick for a second, then go, right? We're assuming they're just going to collide and move apart, okay? So our collisions are going to act like billiard balls or pool balls. They're going to bounce off each other when they collide, okay? And then the 5th postulate of our kinetic molecular theory is that the temperature of the gas depends on the average kinetic energy of the particles. Energy and temperature are hand in hand, right? If the energy of our system goes up, the temperature goes up, and vice versa, right? When we add heat to the system, if we add heat to any system, what happens to our particles? Do they move slower or faster?
faster.
They move faster, right? They have an increased kinetic energy. The more they're moving, the more energy they have, right? So those two things go hand in hand. When we increase the kinetic energy, the temperature goes up. And when we increase the temperature, the energy in particles go up. So those are some things that we have to keep in our frame of mind when we're talking about kinetic molecular theory, when we're talking about gases and things like that. Okay? All right, so let's get into how can we start to calculate some things with gases. And we have to, when we talk about kinetic molecular theory and we talk about the gas laws, we're really looking at relationships and ratios and how these things are connected. So they're typically going to be in the lens of 3 different things. The pressure of the system, the volume of the system, and the temperature of the system. Those are really the 3 variables that we're looking at. Sometimes we look at the quantity and the number of moles, but typically we're going to look at pressure, temperature, and volume. Those are the things, okay? So we have to be really good at dealing with pressure, temperature, and volume. So let's look at how do we talk about pressure and temperature? What are the units for these things? Because volume we're pretty familiar with. What would we measure volume in most of the time, do you think? What's the unit for volume going to be? Liters, good. Could be milliliters, right? Could be milliliters. Could be cubic centimeters, but typically we're going to make ourselves work in meters, okay? Most of the time. I'm sorry, in liters most of the time, not meters. So here's our temperature conversion. This is the temperature unit called Kelvin. Are we familiar with Kelvin? A little bit, okay. To work in Kelvin, Kelvin is a scale that starts at 0 and works its way up. unlike Celsius and Fahrenheit, they have negative temperatures. Kelvin is 0. What is 0 Kelvin called? It has a fancy name.
Absolute zero.
Absolute 0, right? If we reach absolute 0, that means all energy is gone, right? That would be a bad place for us to be, right? Because there's no more energy. So that's no good. Absolute 0 is 0 Kelvin. So if I wanted to convert, let me say this again. 0 Kelvin would be equal to negative 273 degrees Celsius. That's how cold it would be. Okay, so if I want a number in Kelvin, I'm going to take my temperature in Celsius and add 273. That is a really important conversion that we're going to become really good at. So if you need to circle that, highlight that. If that's not something you feel familiar with, let's go ahead and make yourself a note there to remember that one. Okay, we're going to deal in temperature in Kelvin exclusively. So temperature is a must convert. Understood? Temperature is a must convert. Because what is 0 degrees Celsius? What's that going to be equal to in Kelvin?
No.
Just 273, right? Because we're going to take our Celsius and add 273 to it. So if we have 0 degrees Celsius, that would be equal to 273 Kelvin, right? So the reason this is so important is really honestly just mathematically. If I'm doing an equation that I need to divide by the temperature, I can't take something divided by 0 degrees Celsius, right? Can I divide a number by 0? Right, so mathematically it doesn't work. So that's why temperature is always going to be a must convert. It has to get to Kelvin. So that's a must do. This next one is converting from Fahrenheit to Celsius. We're very rarely going to have to do that, right? We don't, in science, we never measure in Fahrenheit. So I put it on there in case we need it, but it's not going to be something we use very often at all. Okay, let's ask the question now backwards. What if I wanted to go from Kelvin to Celsius? What would I do? From Kelvin to Celsius, what would I do? If I wanted to convert from Kelvin to Celsius, what would I do? I would subtract 273, right? I'm using that one right there. So if I had it in Kelvin and it asked for my answer in Celsius instead, I would just subtract 273, okay? So there's our temperature conversions. Those are easy enough. The pressure conversions, we have kind of a conversion, a lot of different ways we can measure pressure, okay? And so I'm going to give you this table, and this one might be one that you want to put on your little formula sheet that you grabbed at the beginning of class. These are all sorts of different ways we can measure pressure, okay? There's 4 different units here. kPa, which is kilopascals. mmHg is millimeters of mercury. Torr and PSI. Those are 4 different ways we can measure pressure. But the unit we like to use scientifically is atmospheres, or ATM is the abbreviation for atmospheres. So we will work to convert pressure to atmospheres a lot, okay? And so that's what these conversions are for. So go ahead and get these written down on your sheet if you want, or they can just stay in your notes. That's fine with me. But we're going to practice some pressure conversions here in just a second, okay? Atmosphere, like I said, is the most commonly used for our calculated values, right? We're going to convert to using atmospheres a lot. It's a common unit in terms of the calculations. But one of the more used units for scientific collection of pressure is kPa, kilopascals. Okay, there's a scientific, instruments that can measure pressure using that. mmHg, do we know what that one is used for? Millimeters of mercury.
Thermometers?
Close, a barometer. Close. Okay, yes, you could be right about temperature. It is measured in mercury as well. But a barometer, I'm going to show you this in a second. A barometer measures the atmospheric pressure. And it's set up just here. Torr is not one that we really see in everyday life. I really don't know when it's used. So we don't use that one. But PSI is maybe one you should be familiar with. Hopefully. Where do we see PSI at?
Air canisters.
Yep. Tire pressure. Yep. Do you know what PSI stands for?
Pressure per square inch.
Close. Pounds per square inch. So the way we measure pressure is how much force is applied over a certain area. So how many pounds of air are per square inch. And that's what it's looking at. But those are the ones that we see. So let's practice a couple pressure conversions here. I pulled up this worksheet. You don't need to have this worksheet. We're just going to do a couple practice ones, okay? Let's try let's try this one. The atmosphere supports a column of mercury that's 748 millimeters in height. What's the atmospheric pressure in torr and in atmospheres? Okay, can you see that okay? Very top one up there. Okay, so we're starting with 748 millimeters of mercury. This is just like a standard conversion that we're really good at. Okay, 748 millimeters of mercury. It wants it in torr and in atmospheres. Now, did you see the relationship on the last one between torr and atmospheres? Sorry, between torr and millimeters of mercury? What's the relationship there? They're the same. So if I was going to look at it in torr, it would just be equal to that, 748 torr, right? Do we see how that works? Mm-hmm. Yes? No? I don't have to do a conversion of that because they're the same relationship to atmospheres. But if I wanted to go to atmospheres from that, I'm just going to come down here and say millimeters of mercury to atmospheres. I know that this is a 1 and 760, and I'm just going to convert, right? And I'm expecting here to have less than 1 atmosphere of pressure because I'm at less than 760 millimeters of mercury. So 748 divided by 760 gives me 0.98 atmosphere. Does that seem simple enough? Yeah. Okay, these are just simple conversions that we know how to do. I just gave you a new list of pressure conversions. Okay, again, our goal for a lot of the equations that we're going to use are to get our pressure in atmospheres. Not always, we won't always have to, but a lot of the time we'll want to do that conversion. So we want to feel pretty comfortable with that. Let's say that we had, let's try this one. Let's try number 9. Normal atmospheric pressure in Mexico City is about 56.5 centimeters of mercury, not millimeters, centimeters of mercury. Convert this to atmospheres. So we're going to take 56.5 centimeters of mercury. And how can we work our way to atmospheres? We need to convert to millimeters. So we're going to go from centimeters to millimeters of mercury. Does anyone know how many millimeters are in a centimeter? That's not a unit conversion that we necessarily memorized, but I think most of you probably know. How many is it?
10.
Yeah, there's 10 millimeters in a centimeter. Think about a ruler, right? It's got 10 markings in between there. So 10 millimeters is 1 centimeter. And then we could say 760 millimeters of mercury is to 1 atmosphere. So that gives us about 0.743 atmosphere. So they have pretty low atmospheric pressure. I'm going to take my starting amount, 90 psi, and I'm going to convert psi to atmospheres and atmospheres to kilopascals. And then I can just fill in my numbers, right? 1 atmosphere 14.7 psi, and 1 atmosphere is, we can just cap this at 101.3. We don't need to take out 3 decimal places there. We're probably okay with that. And then we're just going to convert. Okay, so that gives me 620.2 atmospheres. Does that feel about, does my number seem too big? Or is that what you had?
That's what
That's what I have.
Okay, all right, very good. Now, in all reality, couldn't we just slide this right here? Because we call them equivalent to 1 atmosphere. Yeah, you could, right? If you know that they're equivalent to one another, you could slide that in there, but really whatever you want to do is fine.
So would it be 620.2 kPa or?
Oh, you're right. Thank you. Yes, I just mislabeled my answer. No, you're right. Thank you. Yep. That's why my number seemed too big. That's why I was confused, but yes, you are exactly right. Okay, that makes much more sense in my head. Okay, very good. All right, we feeling okay with our pressure conversions? Okay, so now we know how to convert temperature and we know how to convert pressure. Let's figure out this. I'll show you. A barometer is set up just like this. It's this whole vacuum system with just like a little tray of mercury and a column of mercury. And the atmospheric pressure pushes that tray of mercury, right? It either pushes the mercury down if it's got a high atmospheric pressure, or if the atmospheric pressure is low, the mercury can rise up in that tray, right? And if it presses down, it's obviously going to push it up into the column higher, right? If it pushes that mercury down, it's going to shoot itself up into the column higher, which gives you a higher barometric or atmospheric pressure. Or if the barometric pressure is low, right? If the atmospheric pressure is low, it will allow that column to kind of relax and come back down, right? So that's literally what it means when it says mmHg. It means millimeters of mercury. So it's measuring how tall the column of mercury is, right? That's really it. So 7.6 centimeters, right, would be another way you say it. So they use 780 because that's what 760 because that's what the standard is, right? When they think the atmospheric pressure is standard, the column is 760 millimeters tall, which we refer to as 1 atmosphere of pressure. Okay, that's standard. Okay, good. What are we going to use most of the time? Okay, when we do our problems, sometimes we're told our pressure and our temperature are at a condition called STP. And STP stands for standard temperature and pressure. STP is a set of conditions. So when it says our object is at STP, that means we automatically know the temperature to be 273 Kelvin, and we automatically know the pressure to be 1 atmosphere. Okay, I have them paired a little bit differently, but in all reality, this is the pair I want you to memorize. STP, right, this is the same as 273, and this is the same as 101.325. But I want you to think about it in terms of the units we prefer, right? So when we say when we say our gas is at STP, we automatically know the pressure is 1 and the temperature is 273, right? Those are going to be automatics for us. So STP is a set of conditions, a set of temperature and pressure conditions. Okay, a set of conditions. So we automatically know what pressure is and what temperature is. Okay, so we're going to start looking at now how can we calculate these relationships of gases. The relationship. P1V1 equals P2V2. The 1 and the 2 kind of signal to us that this is the initial measurements and these are the final measurements, right? Kind of the before and the after some change has taken place. That's what we're looking at here with these types of gas laws, is we see a change happen and then we want to measure what's the result of that change. How is the volume affected? How is the pressure affected? Things like that. So in all of these equations we're looking at today, there's going to be a change of some sort, right? There has to be a before and an after. Now, does it really matter if the initial side is on the left or the right of the equation? No, it makes no difference. But we do need to be really careful that we don't mix and match initial pressure, final volume, whatever it is. So we have to be really diligent with our context clue reading here, right? We have to read the problem really closely. So let's try one. 1 liter of a gas at STP is compressed to 473 milliliter. What is the final pressure? Okay, so before we even get into the math, let's make a prediction. Our volume is going from 1 liter down to 473 milliliters. So is the expectation that the pressure will go up or down? I think up as well, right? We're shrinking that balloon down, which means those particles are moving faster, right? It's gonna feel more pressure, okay? So let's kind of start writing out what we have here. As we start getting into these word problems, that's what we're gonna see more and more of these word problems. I think it's really important that we write out the information that we have and try to help us figure out what equation we might have to use, okay? So 1 liter, what variable is that representing for me? Pressure, volume, or temperature? V1, right? Initial volume. So my V1 is equal to 1 liter. Now it tells me my system is at STP. What does that tell me about my pressure? P1 is equal to what? 1 atmosphere, okay? And if you need to write that on your formula sheet, you can, right? STP is equal to 1 atmosphere of pressure and 273 Kelvin. Now, in my problem here, I also know that the temperature is 273 because it's at STP, but is temperature affecting my problem? Is there a temperature change throughout my problem? There's not. So I can write it down, but I'm not going to need it. Right? I'm not going to let temperature affect my problem because there's no change in temperature. So if there's not changing it, we can leave it out of our problem. Okay, 473 milliliters is the next number in my problem. What variable does that represent? V2. Okay, are we seeing any red flags here?
It's in milliliters.
It's in milliliters. Okay, now here's what I'm going to tell you. It makes no difference for these problems, these Boyle's Law problems. It doesn't matter if our volume is milliliters or liters, but it needs to be the same on both sides. That's the rule, right? It doesn't have to be one or the other, but it needs to be the same on both sides. Is that clear? Okay, for our own practice, I want us to, if we get to make the choice, I want us to go to liters because that's what we'll need in later equations that we use. So if you get to make the choice, I would take it to liters. If both of them are milliliters, leave them, right? No need. But if you have to change one, let's change them to liters. So how can I get this 473 mils? How do I get that to liters?
Point in front of it.
Okay, I need to move it 3 places. I need to move the decimal 3 places. So 1, 2, 3, that makes it 0.473 liters, right? Essentially, I divide by 1,000. What is the final pressure? That means P2 is going to be what we solve for. I'm going to encourage you to write that down with its question mark, right? That's what we're solving for. It's really important for us to have a clear vision of where are we going with our problem. Because sometimes we write down the numbers and then we're not even really sure where to go from there, right? Asks me for final pressure. That's what I'm solving for. Okay, so my equation is P1 V1 equals P2 V2. And now I'm just plugging in my numbers. 1 atmosphere times 1 liter equals P2 times V2. Okay, so mathematically, all I'm doing here is taking 1, which is the whole left side of my equation, divided by 0.473, and I get a final pressure of 2.11 atmospheres. And does that match the prediction we made? Did we anticipate our pressure to go up, to increase? Yeah, I think we did, right? We predicted that our pressure would rise, and it did. Okay, this says I have 5.6 liters of a gas in a piston. Do you know what a piston is? Yeah, exactly. It has kind of interchangeable volumes, right? It can move. Usually it's a movable piston, right? It can move back and forth. Okay. It has a pressure of 1.5 atmospheres, and I compress the gas until it has a volume of 4.8 liters. What will the final pressure inside the piston be? Okay, this problem is set up actually very similar to our last one. We won't always be looking for final pressure, but in this case we are. So I'm going to go through and start labeling my numbers. So 5.6 is V1. My initial pressure is 1.5 atmospheres. I compress it until I have a volume of 4.8 liters, and I'm solving for P2. That's my question mark. Okay, so if we're going to set up our equation, we'll take 1.5 P1 times V1 equals P2 times V2. Right, everything is multiply and divide. So we're going to make sure we do our math correctly here. And we get a final pressure of 1.75 atmospheres. And that is an increase from our initial pressure. Does that match the expectation? Right? We decreased our volume, right? We squished it down, which would make sense that our pressure increased. Okay, very good. Any questions so far as we're working through these? Okay, let's try one more here with Boyle's law and then we'll move to the next. A balloon is filled with 835 milliliters of air at a pressure of 782 millimeters of mercury. If I add 424 mils of air to the balloon, what will the final pressure be? Okay, we've got different units here. Is it okay to keep our units as they are? We have milliliters as our volume unit, and we have millimeters of mercury as our pressure unit. Can we keep them as is? Yeah, we can, right? Because our volumes are both mils, and our pressure is millimeters of mercury, but my answer doesn't specify it has to be in atmospheres, which means we can just keep it, and our answer in pressure will also be millimeters of mercury. Does that make sense? Right, we can just keep it. So let's kind of walk through what we have. We have our initial volume. So V1 is 835 mils. P1 is 782 millimeters of mercury. Volume 2, what is V2 going to be? Is it going to be 424? It's not, right? Because here's a context clue. It says we add 424 mils. So we're pumping more gas into it, right? We're increasing our volume and we're adding that much air to our balloon. Does that make sense? So my final volume is not 424. We're increasing the volume of the balloon. So our final volume is really going to be 835 plus 424, right? Does that make sense for everybody? Mm-hmm. Context clue that's very easily missable if we're not really, really diligent about reading that closely. So that's what I'm talking about with these word problems. We really want to be, diligent about our reading, right? Making sure that we're understanding what the question is asking and putting things together correctly. So again, we're solving for final pressure. I don't know. Sorry, I must have just been in a groove that day. I was making my slides, but that won't always be the case. 782 times 835 equals P2 times 1259. 1259 milliliters is my final volume. So now we're just going to do the math. I got a pressure here of around 521. Does that match what anyone else had? No?
I had 518.
Oh, I plugged in the number wrong on my calculator. Yep. Okay. Let's try this again. Oh, goodness. Okay. I'll go with what you had. What'd you have? 518 something?
518.6.
518.6. Okay, very good. Millimeters of mercury. Now, this, compared to our initial pressure, was a decrease. Does that match what we thought? Volume went up, so pressure goes down, right? They are inversely related. If one goes up, the other goes down, and vice versa. So are you feeling okay about that? Okay. All right, so that's Boyle's law. Okay. The next one we're going to look at is Charles' law. And this is the relationship between volume and temperature. Volume and temperature. Now, in order for us to study this relationship exclusively, we have to assume that pressure stays constant. Okay, so we are under the assumption that the pressure of our system is unchanging. If we're studying just volume and temperature relationship, pressure has to remain constant. So when we do that, we see that these things are directly related, right? Inversely related would look something different, right? If one goes up, the other goes down, like this, right? That's what an inverse relationship would look like. But a direct relationship means if one of them goes up, the other one goes up. Okay, so if we see an increase in temperature and our pressure remains constant, those particles are moving faster and faster, which is pushing the balloon bigger, right? That's really what we're looking at there. So here's the equation for Charles' law. Okay, let's go ahead and put that on our formula sheet, on our equation sheet. V1 divided by T1 is equal to V2 divided by T2. When you look at this equation, I think it becomes really clear why converting to Kelvin is so important. If we have an STP system, that would mean 0 degrees Celsius. And I cannot divide, we already said, we can't divide by 0. So that's why converting temperature is so important, right? And it's not, here, one more addition with that, is that it's not a conversion like milliliters to liters or something like that, where it's a multiplication conversion. It's an addition conversion. So that's why even more so it's important that we're in Kelvin on both sides. If we have two things that are in milliliters on both sides, mathematically it doesn't matter, because if we were going to put them in liters, it'd be like dividing both sides by 1,000, right? That mathematically is the same. But an addition conversion doesn't necessarily it doesn't necessarily affect both sides the same, right? When we add something to each side, it doesn't exactly affect it in the same way. So we just need to make sure we're careful with that. Temperature is a must convert. All right, here we go. I have 67 liters of helium in a balloon at 28 degrees Celsius, and I increase the temperature of the balloon to 47 degrees Celsius. What will the final volume of the balloon be? Okay, so let's make a prediction before we even get into the math. Temperature, what's temperature doing here? Up or down?
It's increasing.
Temperature's going up, so what do we think volume's going to do?
Getting it down.
It's going to go up. These ones are directly related, so they're going to go do the same thing. One goes up, the other goes up. Okay, so let's see if the math tells us that. V1 is 67. T1 is in Celsius, so how do I get that to Kelvin? What's my conversion to get to Kelvin? What do we have to do?
Add
Add 273.
Add 273. So 28 plus 273 comes out to be 301 Kelvin. And you don't use a degree for Kelvin, it's just Kelvin, right? It really means business, I guess. Okay, no degree symbol there, just Kelvin. T2 is equal to 47 degrees Celsius. We're going to add 273 to that as well. And I get 320 Kelvin. What will the final volume be? So that's going to be my question mark. All right, so let's go ahead and set up our equation here. V1 over T1 equals V2 over T2. Do we know the math we have to do here in this proportion type system to be able to solve for V2? What's your math cadence here to work through proportion like that? Do you remember?
cross multiply
Cross multiply and
and divide.
divide, right? So if I want to get through this math problem, I'm going to cross multiply and then divide. Does that sound familiar to everyone? On a proportion like this, right? We're looking at how are these things related. So we cross multiply, right? I leave our unknown out of it. Cross multiply and divide. Okay, so 320 times 67 divided by 301. And I get a volume here equal to 71.2 liters. And it was our expectation that volume would go up, right? Which it does, from 67 to 71. The combined gas law. Cleverly named the combined gas law. Okay. But what is it? It's truly just a smush of all three things. Because if we look at it, here's Boyle's law. Here's Charles' law. And here's Gay-Lussac's law. Right? They're all just smushed together. But now it allows us to look at condition changes when there are multiple changes happening. Right? If our pressure and our temperature are increasing, or if our volume is going up and our temperature is going down, right? It gives us a more whole picture. But here's the reality. If you're going to memorize any of your gas laws, it should be this one, right? This one and probably only this one. Because if I'm doing a gas law problem and they don't mention pressure, I can just leave it out and then I'm left with Charles' law. Right? Or if there's not a temperature change, I can leave it out and I'm left with Boyle's law. Right? Do you see what I'm saying? So if there's one that you should know, it should be this one. Because it's just a culmination of all the other ones put together. Okay? All right. The algebra can get a little stickier here, right? If we're looking for this, we're still going to cross multiply, divide, and divide. Right? It can get a little bit stickier, but it's still very doable. Okay? Maybe just not in one clean step. All right, let's try one. We're going to have to be real clear about what our variables are here. Keep ourselves nice and organized because our word problems get a little bit longer, right, with combined gas law. So a balloon has a volume of 1.8 liters. That's going to be V1, 1.80 liters. The temperature of the balloon was okay, I think mine prints funny here. Does yours say 20 degrees Celsius or 200?
20.
Okay, yeah, see, this is supposed to be my degrees sign, but okay, all right. This happens to me every year, and every year I forget about it. So they do the whole problem, and then someone remembers to tell me, Mrs. Noll, it's supposed to be 20. Okay, 20 degrees Celsius, and that means this one is probably negative 10. I'm assuming?
Yes.
Okay, very good. So let's keep those in the right. Okay, so my T1 is 20 degrees Celsius. Can we keep it? Can we keep it in Celsius? No. Let's take it to Kelvin, which would be 293 Kelvin. Okay. The pressure was 1 atmosphere, so P1 is 1. The balloon rose 3 kilometers into the sky. Do we care about that? Does that go into our gas law problem? It does not, right? We don't care. Okay, the pressure now becomes 0.667, and the temperature is negative 10. So that means T2 is not 273, but it's 263 Kelvin. Agreed? That leads us, can we see here that that's a 30-degree swing? Right? We also see here is a 30-degree swing. So we can kind of make sure that we did our math right. Okay. What would the new volume be? So V2 is going to be our question mark. Now, could you just pull from your problem and put things directly into your equation? Absolutely, right? If you feel comfortable just throwing things into the equation right away, by all means do it. But I think it's important to be able to see the vision of where are we going, right? Writing down at least the question mark variable, I think is important. Because otherwise you'll start putting numbers in and then realize I don't have anything to solve for because you put in a number wrong or something went sideways. So just do that for me, okay? All right, let's go into our equation. P1 V1 over T1. So 1 atmosphere times 1.8 liters over T1, 293, equals P2 times V2 over T2, 263 Kelvin. Now, mathematically, there's a lot of ways you can go about it. For me, it's still easiest to just cross multiply and divide. You just got an extra thing here at the end. Okay, so in my calculator, I'm going to cross multiply, divide by 293, and then I'm still going to take this extra guy, and he gets divided as well. So cross multiply, divide. Okay, that diagram looks a little funny, but do it your way, and let's see if we get the right answer, because I want to make sure everyone's doing this correctly in their calculator. So I want everyone to plug it in and get an answer out so we can make sure that we match.